And then let me also introduce two other concepts, in fact three other concepts. One is the integral form of the hypergeometric functions, and also look at the hypergeometric functions for two variables x and y, and also introduce certain special integrals known as the elliptic integrals, right. So, the first discussion will involve the integral forms of hypergeometric function. Okay. So, the first form that is useful for us is the following: f of a b c comma 1 minus z is gamma of c by gamma of b times gamma of c minus b, integral 0 to infinity s of b minus 1 plus s of a minus c times 1 plus s z to the power minus a ds. Okay. Okay. So, then the other relation that will be useful for us is f of a b c of 1 by z is gamma of c by gamma of b times gamma of c minus b, integral 1 to infinity s of a minus c s minus 1 of c minus b minus 1 s minus 1 by z to the power minus a ds, right. Okay. And then there is another relation, that is the relation of symmetry, that comes right from our series representation of the hypergeometric function. We also see that there is a symmetry involved in this function. We see that f of a b c of z is also f of b a c of z. Okay. So, a and b can be flipped. Okay. And then the fourth important relation is the relation by a mathematician Ardeli, which is the double integral form. The double integral form by Ardeli, and this is given as follows. So, f of a b c z is gamma of c square divided by gamma of a gamma of c minus a times gamma of b gamma of c minus b, okay, times the double integral. So, times the double integral of 0 to 1 t to the power b minus 1 times tau to the power a minus 1. So, since we have two variables of integration, these are t and tau. So, t to the power b minus 1 tau to the power a minus 1 minus t to the power c minus b minus 1 times 1 minus tau to the power c minus a minus 1, right, and then integral with respect to dt and d tau divided by 1 minus t times tau times z to the power c. Okay. Okay. So, then I am also going to introduce the hypergeometric function of two variables, and we will look at a special form of these two variable functions known as the Appel's form. So, hypergeometric function for two variables, also known as the Appel's form. The Appel's form, f 1 of a comma b prime comma c comma x comma y is double summation m from 0 to infinity and n from 0 to infinity of a, the Pochhammer symbol a of m plus n, b of m b prime n by m factorial n factorial c of m plus n times x to the power m times y to the power n, right, and this is also equal to the gamma of c can be written in the integral form. So, the integral form is gamma of c by gamma of a times gamma of b. Well, we do not have a b outside. So, this is gamma of c minus a, right, and times the integral 0 to 1 t to the power a minus 1 minus t to the power c minus a minus 1 times 1 minus t x to the power minus b times 1 minus t y to the power minus b prime dt. Okay. So, that is the integral form of the hypergeometric function of two variables. Okay. So, then some useful relations for this Appel's form. So, along this line I am going to mention some useful relations between the Appel's form or the two variable form and the regular form or the one variable form of the hypergeometric functions. Okay. So, the first relation can be checked quickly is that the Appel's form f 1. So, I denote my Appel's form as f 1. So, f 1 of a comma b prime comma c comma x comma 0. So, let us say we set one variable to 0 can be seen to be equal to the regular hypergeometric function f of a b c comma x. Okay. Setting one variable 0 will bring back to our one variable hypergeometric function. Similarly, if we set the other variable, we will again look at we will see that we will get another form of one variable hypergeometric function. So, if we set the other variable 0 f 1 of a comma b prime comma c comma 0 comma y, this is f of a comma b prime comma c comma y, and that is it. So, in general I can write down my hypergeometric function of two variables for the general case as an infinite sum of hypergeometric functions of one variable, right. So, in general my Appel's form can be expressed as an infinite sum of the ordinary hypergeometric function. Okay, as follows. So, f 1 of a comma b prime comma c comma x comma y can be written as the following sum. This is summation m from 0 to infinity of the Pochhammer symbol of a m b m by c m times the hypergeometric function of a plus m comma b prime comma c plus m comma y times x to the power m. Okay. So, that is what the summation is. So, finally, let me also introduce the relations of the so called elliptic integrals. Okay. So, we have seen these elliptic integrals earlier when we were describing the solution of the bent beam problem or elastica. So, let me now quickly elaborate on these functions. So, I have written down the elliptic integrals of first, second and third kind. So, elliptic integrals. So, the first kind has the following form f of phi comma k is integral from 0 to phi of dv divided by 1 minus k square sin square v. Okay. The second kind The second kind is given by E of phi comma k. In fact, this is the kind that we have used in our description of bent beam problems earlier. Integral from 0 to phi of square root 1 minus k square sin square v dv, right. So, k is from 0 to 1 and phi is from 0 to pi by 2 and alpha is from minus infinity to infinity. Okay. Okay. So, and then my elliptic integral of the third kind is pi of phi comma alpha square comma k. This is integral 0 to phi dv by 1 minus alpha square sin square v times square root of 1 minus k square sin square v. Okay. Okay. So, with regards to these three elliptic integrals, I have also some useful relations. So, let me say that my function capital K of k is the elliptic integral of first kind evaluated at phi equal to pi by 2 comma k, and my E of k denotes the elliptic integral at pi by 2 comma argument at k, right. So, then I have some relations which we will be using while we solve while we integrate our model equations. The relations, one of the relations is the Legendre relation. The Legendre relation, which states that E of k times k of k prime plus E of k prime times k of k minus k of k times k of k prime, this is equal to pi by 2, and we have more properties of the form f of 0 comma k is E of 0 comma k is 0 and f of phi comma 0 is E of phi comma 0 is phi, and E of phi comma 1 is sin phi, and E of well we have f of phi comma 1 is log tan phi plus secant phi. Okay. Okay. So, these are my relations that we will be using in our later development of the model. Okay. So, this is so far the basics that I have covered in terms of the special functions. Now, my next set of lectures are going to cover some basics in physical chemistry, namely the introduction of interaction energy, the van der Waal interaction energy and the so called Lennard-Jones potential. Okay. So, let me just introduce some basics in physical chemistry. So, again these basics are extremely rudimentary in the form that almost all students taking this course must have done certain high school science courses. Okay. So, I am just revising some of these basics of physical chemistry. Okay. So, let me start with the concept of interaction energy. Interaction energy. So, when I talk about interaction energy, I talk about the interaction of two non-bonded structures. We do not talk about bonds like covalent bonds, ionic bonds and so on. We just talk about the energy of interaction between two structures, for example, two molecules, two compounds which are not bonded to each other. Okay. So, this is I denoted by shorthand IE, and these are for two separate non-bonded non bonded molecular structures. Okay. Okay. So my interaction energy, well, if I want to find the interaction energy of many structures, we could either use the discrete application where we can individually sum the interaction energy, or if this distribution of the structures are nearly homogeneous and the distance is infinitesimally small, then possibly we could use as the interaction energy in the form of an integration rather than a summation. So what I just said is the following. So for discrete applications, I can sum the interaction energy per atomic pair, right, or sum the interaction energy per structure, where my net interaction energy is E is given by summation, double summation I j of phi of rho I j, right, where my phi of rho I j is defined as the potential or the interaction potential function for, well, for my atom pairs I j. Okay. So, rho I j is the interaction potential for atom pair I j, and located at rho I j apart, Okay. So, then for continuous applications I can change my double summation as double integral. For continuum applications, I can, assuming that atoms are uniformly distributed over the entire range of surface. Essentially, we do not want non uniform distribution, otherwise the integration may not hold or may not make sense. So, assuming the atoms are uniformly distributed over the entire range of the surface, then I can describe my interaction energy I e per atom pair as follows. So, my E is double integral of over surfaces S1 and S2. So, these are my atomic pair surfaces of phi of rho times dA1 dA2, right. So, I am talking about the atomic or the two pair structure interaction, and then I take the integration of these pair structures, right, and also these are multiplied by the number of atoms per unit surface or number of structures per unit surface. So, where my eta I is the mean surface density of atoms or structures on the ith molecule, okay, and my SI is the surface of the ith molecule. Okay. So, which means eta I is the number of atoms per unit surface of the structure we are considering, the ith structure, right. So, that is the interaction energy per pair. So, let me highlight this concept with an example. Okay. A very basic example of a graphene sheet, right. We know that graphene sheet, again this is basic class 12th physics. We know that graphene has at the molecular level, graphene has hexagonal structures, and also graphene is arranged in such a way that each of these structures are arranged in sheets. So, we have the arrangement of graphene is in the form of sheets, and that is why graphene is very slippery. Okay. So, let me look at a hexagonal structure of graphene. So, we have typically in a sheet, let us say this is a sheet of graphene, we have hexagonal structures of graphene, where each of these vertices of the hexagon are occupied by carbon atoms. These are also so, let me just extend these structures, right, and so on. So, notice that if we were to look at each of these joints, these one joint which is occupied by one carbon atom is shared by 3 hexagonal rings. So, ring like 1, like 2, like 3, right. So, which means that since there are 6 carbon atoms in one ring, so essentially the number of carbon atoms which per ring will be 6 times 1/3 or 2 carbon atoms per ring, because each carbon atom is shared by 3 rings. Okay. So, which means the atomic density per molecule of the graphene is 2. Okay. So, the example says find the surface density of carbon atoms, on a sheet of graphene. Okay. So, let us say so we know that graphene, again this is class 12th physics, graphene consists of the hexagonal rings or the so called tessellated hexagonal rings, consists of tessellated hexagonal rings, right, and so that each atom in the ring is bonded to two other rings, which means that my atomic density eta will be 6 atoms times 1/3, because shared by 3 different rings divided by the surface of one ring, let us say A hex or A hexagonal. So, I see that my eta comes out to be 2 by A hex, or where area is the area of one hexagon, right, and that gives me my surface or the number of atoms per unit area of the ith ring of the graphene. Okay. So, where my A hex is the surface area of one ring. Okay. So, then let me also introduce, once we have introduced the concept of interaction energy, let me also look at the specific interaction energy known as the van der Waal interaction. So, again van der Waal interactions are non-contact interaction, or unlike the interaction like covalent or ionic interactions. So, these are non-contact interactions. So, van der Waal interaction energy, these are either attractive or can be repulsive, right. We will look at a specific form of the interaction potential which models this attractive / repulsive interaction energy. Namely, we will see that if the atoms come very close to each other or almost touch each other, this interaction energy becomes strongly repulsive, and when they move slightly away from each other, they become attractive, and then the amount of attraction falls away exponentially, or falls away exponentially, fine. So, as I just said, these are attractive or repulsive interactions and these are non bonded. Okay. And non bonded between two or more molecules. Okay. So, I am not going to go into extreme depth of these interaction energy, I am going to just highlight the basic mechanism or the philosophy of these interactions, which is useful for our model development. Students who are more interested again can look at some of the basic school textbooks in physical chemistry. Okay. So, these are non bonded interaction between two or more molecules, also known as the intermolecular forces. Okay. So, then once we have the van der Waal interaction energy, I can describe my van der Waal force. My van der Waal force is the gradient van der Waal force. Van der Waal force is between two non bonded atoms, is the gradient of the interaction energy, right, is the gradient where E is my interaction energy. Okay. The van der Waal interaction energy, I have put a minus sign, so that to represent that this force is an attractive force. Okay. Okay. So, then let me start, let me highlight this interaction energy with a quick example. So, for example, suppose let us in fact look at the example that we are eventually interested in. So, suppose we are given a cylinder, let us say a carbon nanotube, right, and we want to and we are also given the interaction energy of the carbon nanotube with some surrounding particles. So, these are all cylindrically symmetric objects, and I want to find the interaction or the van der Waal force of the carbon nanotube with its surrounding objects. Note that due to cylindrical symmetry, the radial components of the force, they completely balance out each other, and the only force that we will have will be along the axial direction or Fz, right. So, suppose my molecule, which is the molecule that we are after, is rotationally symmetric. My molecule is rotationally symmetric, right, around the z axis. My molecule is rotationally symmetric around the z axis, then the resultant force is in axial direction. The resultant force is in axial direction, right, and my F of van der Waal V dW is given by negative of the interaction energy with respect to the axial direction z, and this has the direction k hat. So, my k hat is the following direction that I have shown in the figure. Notice that along R all the components of the force, they cancel each other. Okay. So, again negative sign means attractive, and along forces along all other directions cancel, right, and that is easy to see. Okay. So, then so once I have described my van der Waal interaction energy, let me also describe the so called Lennard-Jones potential, which describes this van der Waal interaction energy. So, Lennard-Jones potential has a very specific form, and it represents this attractive repulsive type of an interaction versus the distance between the two atoms or structures.